Raw enterprise supply chain data is inherently chaotic. The daily reality of commerce is defined by erratic sales spikes, localized stockouts, and unpredictable supply shocks. To execute physical operations, that noise must be forced into absolute structure. Planners typically interact with SAP Integrated Business Planning through a cloud-based spreadsheet interface. This environment provides the familiar ergonomics of Excel, designed for manual adjustments and consensus reviews across the organization. The system's actual logic resides in the architectural layer beneath that UI. SAP IBP serves as an execution wrapper for a continuous, high-density statistical data pipeline. Transforming noise into execution requires this 5-node SAP HANA pipeline. Data moves sequentially: diagnostic statistics, predictive time series, short-term state updating, stochastic probability, and operations research. To understand this architecture, we will trace a single data signal from inception on the left to factory execution. Operating effectively in this environment requires abandoning the concept of IBP as a static database. It is a chronological, algorithmic lifecycle. We begin inside Node 1, where the operational reality of raw transactional data is confronted. Feeding unadjusted ERP data directly into a forecasting model causes severe distortion. Artificial market shocks, plant shutdowns, and one-off promotional pushes will corrupt the output. The first algorithmic defense is outlier detection. As this chart shows, the system applies parametric z-scores or non-parametric interquartile ranges to establish threshold limits. When historical anomalies exceed these statistical bounds, they are mathematically clipped and replaced with moving averages. But anomalies are only half the problem. Supply chains also carry service parts and enterprise machinery with lumpy or intermittent demand. In these data sets, historical periods of zero demand heavily outnumber active sales. To solve this, IBP automatically classifies SKUs across two axes: the average demand interval against demand volatility, represented by the square coefficient of variation. When an item plots into the highly intermittent quadrant, standard exponential smoothing is discarded. Instead, the system invokes specialized probability models, the Croston method and the Syntheto-Spoilin approximation. Watch the formula's logic. Croston mathematically decouples the expected demand size from the interval between purchases, projecting a deflated baseline across quiet periods. This diagnostic layer acts as a strict mathematical filter. It ensures that the predictive engines downstream receive a purely structural demand signal. With the noise stripped away, the sanitized data signal flows into Node 2. The objective here is extrapolative prediction, projecting an unconstrained 18-month baseline consensus plan. Relying on a single algorithm for an entire portfolio is a statistical liability. Instead, this architecture splits the incoming signal, routing the data through a parallel competition of complex extrapolative and nonlinear models. Track 1 utilizes triple exponential smoothing, or Holt-Winters. It decomposes history, iteratively updating smoothing equations for level, trend, and seasonality to minimize error. Track 2 handles autocorrelated data using SARA-MAX. It differentials the signal for stationarity, factoring in exogenous variables like price changes directly. Track 3 handles extreme complexity. For nonlinear variables like severe weather combined with product cannibalization, IBP leverages gradient-boosted decision trees, deploying XGBoost through the HANA engine. Running dozens of advanced models simultaneously requires an impartial referee. This is the automated model selection engine. The engine scores every model against a test horizon, comparing predictions against actual outcomes using strict penalties. It calculates the Akaike information criterion to penalize over-parameterization and root mean square error to tax variance. Failing algorithms are terminated. The lowest penalty proceeds. By automating the mathematical selection, the system removes human bias from the baseline and scales to manage millions of individual SKU combinations concurrently. We now have a mathematically sound 18-month strategy, but execution happens in the short-term horizon of the next 1 to 8 weeks. We move to Node 3. The rigid monthly forecast generated in Node 2 immediately clashes with daily operational reality. Highly variable telemetry, open customer orders, point-of-sale data, and shipment delays streams in constantly. Attempting to rerun a massive batch regression every single day to account for these daily shifts would destabilize the entire enterprise plan. To process telemetry, demand sensing uses a recursive least squares filter. A mathematical bracket slides across the data, measuring real-time variance against historical bias. As new data arrives, it executes a state update, instantly micro-adjusting the delivery curve based on the latest error. Demand sensing acts as the statistical bridge. It reconciles what the enterprise mathematically planned to happen with what is actively arriving on the loading dock today. The pipeline now enters Node 4. This marks a profound shift in the architecture, moving away from extrapolative prediction and directly into stochastic probability. This is the domain of inventory theory. Safety stop exists to buffer the stochastic uncertainty of demand and lead times. Without precise calculation, minor demand fluctuations at the customer level amplify violently as they travel upstream, causing what's known as the bullwhip effect. To quantify this at a single location, the system treats demand and lead time as independent random variables. It combines their mean and variance using the law of total variance to calculate exactly how much volume is at risk during a replenishment cycle. From there, a business objective, like achieving a strict 95% fill rate, is run through the unit normal loss function, translating a percentage goal into a specific, mathematically justified unit target. Modern supply chains are rarely single locations. They are interconnected, multi-echelon networks of suppliers, factories, and distribution centers. Calculating safety stock for each facility in isolation guarantees the bullwhip effect, saturating the network with redundant inventory buffers. Node 4 solves this through multi-echelon inventory optimization, or MEIO. Rather than treating nodes as silos, the system calculates the service time trade-offs across the entire directed graph simultaneously. Executing network-wide cost minimization, the optimizer computes that storing raw materials upstream carries drastically lower holding costs. By calculating lead time interdependencies, the system deliberately increases upstream safety stock, instantly eliminating the mathematical need for dozens of expensive, isolated regional buffers. Here, probability theory is weaponized to protect working capital. The company ensures it never pays to buffer the exact same uncertainty twice. The signal reaches the final node. All prior forecasts, real-time demand adjustments, and stochastic buffers exist as pure mathematical requirements. They must now be converted into a rigid physical schedule. This conversion is executed by the IBP Supply Optimizer, an engine built on mixed integer linear programming. At its core, the algorithm must solve this, a massive global cost minimization objective function. It assesses the precise financial impact of production overtime, transport fees, holding constraints, and stockout penalties. It continuously computes trade-offs. It weighs the exact cost of expediting components via air freight against the localized penalty of failing to deliver to a priority customer. But an optimal mathematical minimum is useless if it violates the laws of physics. The algorithm must solve the objective function strictly within the boundaries of physical constraints. First, it enforces flow conservation, ensuring strict mass balance at every node, product, and period. Inventory cannot magically appear nor disappear. Second, it applies discrete resource capacity constraints. By utilizing binary integer variables, the system prevents the schedule from ever exceeding maximum machine labor hours or violating minimum production lot sizes. Solving a matrix of this size requires immense computational density. SAP HANA executes advanced branch and cut interior point algorithms directly within its memory layer to find the optimal global state. The output is an exacting directive. It tells a plant manager exactly what SKU to build, on what specific machine, at what exact hour. This final operations plan represents a mathematically optimal state, bounded strictly by the physical limits of the supply chain. Zooming out, we see the architecture functioning as a continuous mathematical pipeline. The noise is diagnosed and cleansed, the baseline is predicted, the short-term variance is updated, the uncertainty is buffered by probability, and the network is mathematically constrained. Processes that historically required dozens of analysts working in disconnected silos for weeks are now executed concurrently across millions of data points within the HANA framework. By linking these distinct statistical domains into a single cycle, SAP IBP functions as a unified decision-making environment. It allows the enterprise to move from reactive guessing to a state of optimized readiness, stabilizing execution in the face of future volatility. In a highly volatile global market, an applied statistical pipeline is the only defensible barrier against operational collapse.